This first problem in this homework set is really a simple integral problem that we would have seen in Calc 2, where we're just integrating the sine of 9x. And technically, we don't think about this as a separable differential equation, but it is a differential equation because it's an equation that contains a function that you're trying to solve for, whose derivative exists here, and it's the first derivative of y with respect to x is equal to this, and so we can technically separate it. So all the stuff that we did back in Calc 2 is essentially a separable differential equation. We're all separable differential equations. Some differential equations might look a little bit different. You know, a differential equation, again, is an equation where we're trying to solve for a function whose derivative exists in the equation, at least the first order derivative. But sometimes we see the differential equation written a little bit differently from what we're used to. And we're not so used to seeing this dx, dy written separately. But what this is essentially is an equation with differentials. And there's a little portion in Calc 1 where we study differentials, and a lot of times professors skip it. I normally skip it, or I just breeze through it. But it does become an important part in talking about some of the mathematics behind dynamics and things like that. But sometimes we can see an equation, a differential equation written this way. So let's take a look at that. And with our tools or our ideas for solving for a separable differential equation, this is like almost a step has been taken for us already, in that the dx and dy are already separated, and we just need to deal with it. So let's do this problem, and we'll check our answer too. I'll punch in my answer, see if it's right. And we'll separate it. So the dx and the dy are here, and if we just go with the convention, it looks like our y is going to be our independent variable, and our x is our dependent variable. So what I'm going to do is I'm going to get y or dy by itself, and there's no other dy's to put along with that. So I'm going to have a negative dx, and then I'm going to divide both sides by e to the 7x. So instead of writing that as a denominator, maybe I'll write it as e to the negative 7x. With the exponent negative, it's like being down in the denominator anyways. And then I would integrate both sides. So let's take the integral of both sides. And then I would have on the left-hand side, it's just y. The plus c that would come up on the left-hand side, I'll just merge in with the plus c on the right-hand side. I have negative e to the negative 7x. Is it times negative 7? So divided by negative 7, right? So u substitution would clear that up in case it's not that clear yet. But that's what it would be, and then a plus c at the end here. So this essentially becomes a positive, and that's your solution. There's no initial conditions here, so I think we're done. So your y of x is equal to 1/7 e to the negative x, 7x plus c. All right? And a lot of you, seems like a lot of you have already worked on the homework problems, so just for checking, let's see how this will work out. So my answer requires us to put some sort of formula, not just a number, not just multiple choice. So when I click on this box over here, you'll see a calc pad, it looks like. And you can use a calc pad, or you can just use keyboard for most of them. So I think we have a 1/7. If I were to type in 1 divided by 7, it'll automatically create that fraction for me. And then I'll right arrow, and then I have an exponential function, and then I'll just use the caret, and then that already puts me up in the thing instead of looking for, the the appropriate symbol for that. So caret up here and negative 7x. And then don't forget your plus c. So I right arrow again, and I'll put a plus c. And I don't know if they're concerned about having this capital or lowercase c. Let's see. Submit answer. It looks like it's good. If you would have put a capital C, that would work too. What if you forgot the C? That would be wrong. Like A? I'm just messing around here now. I'm just wasting time. All right, so it'll take a lot of different answers. So I think this is pretty flexible in terms of putting in your correct answer. So if there's if you're trying to put in an answer and it doesn't look correct, so you just make sure that you're inputting things correctly. And then you want to also make sure that your answer is actually correct. And so if you have a big issue with that, then just send me an email. I'll try to check up. I need to know the problem set that you're working in, the actual problem that you're working on, and then I'll observe it. Okay. So some of these get a little bit more complicated. This looks complicated. I don't know if I want to do that. Now let's try to do it. So some of these separation of variables requires a little bit more of a trick to it. Let's see if I have any of those tricks in my notes. Nope, no tricks. Silly rabbit.
Really?
Sorry. Is that commercial even on anymore? So the other interesting part about this particular problem is that we are given a heads up for a solution. It looks like our solution is going to be written like this. That's kind of strange. That's how would you describe your solution here before even doing this problem? It's implicit, right? Remember the word implicit? So that you can't get y by itself. I mean, you could try, and then you'll probably get some other weirder looking answer. But this idea that you're going to take it to the 7th power, it's going to make this a little bit more difficult to deal with. So it looks like we want our answer to somehow look like this, and somehow look like this. How's that going to work? So let's see if we could do this. It doesn't look like it's that easy to separate either. It looks like we can, I say when you separate things, you can, if you're adding and subtracting, you're going to have more problems separating your variables. Okay, so we have to try something a little bit different. Has anybody figured out how to begin yet? Yeah.
So if you're separating it, can you just simply like take that old denominator and put it to the other side, like multiply?
Yeah. Well, the hard part is that the denominator has both x's and y's in it.
So say you multiply dx to both sides, and you're just taking the integration with respect to y. So you're just like
No,
you
you can't do that. Yeah. Yeah.
Can you do like x times y over all that denominator plus or x?
You could break that up, but the hard part is that because our denominator is another, we need that as part of what we're dealing with. Yeah. So really, if you've tutored algebra recently, that's probably the only time this idea will come up. You guys remember factoring by grouping? Usually works well with 4, and it usually has to be set up nicely. So this is a setup, is what it is. But that's okay. Factor by grouping, if you remember that, is especially when you have 4, usually when you have 4, you take 2 of them at a time, you factor that out, and then you take the other 2, and hopefully when you factor that out, there's going to be another factor in common. So that's what's, looks like that's what might happen here. So if we factor by grouping, let's factor out an x from the first one. I get a y plus 4. And if we can factor out a -1 from the second one, I'm going to get a y plus 4. So there's my nice setup for the factor by grouping. I can factor out a y plus 4 up on top, and then I get an x minus 1 left. And now the denominator hopefully will work out almost the same way. So I'll take out an x, I guess, x, y minus 3 left, and I'll take out a 6, and then a y minus 3 again. That's perfect. X plus 6, y minus 3. Is that right? So now I think you can separate this quite easily because you're multiplying and dividing. So let's collect all the dy's on one side. So separate dy on this side. Let's see. So all the y's that were in the numerator go in the denominator because I'm bringing it over to the other side. And in the numerator, y minus 3 over y plus 4. So it looks like you just switch the numerator and denominator business. And then on the other side, I would have my x's together, and that would remain the same, x minus 1, x plus 6 dx. And you should be able to integrate this. Doesn't look like an easy integral, but it should be manageable, maybe. So there are several ways to do this. One way is to separate it into y divided by y plus 4 and then -3 divided by 3 plus 4. Another way is do a u substitution for the y plus 4 and then replace that y up on top and then change it back in terms of u or whatever. And then another way to do this is to punch it in Wolfram alpha and get an answer.
So unlike
Guess what I'm going to do?
or you can have it solve that.
Sure. You guys could solve this, right? Yeah? All right, let's go old school here. I haven't taught Calc 2 in a while. So let's try it out using that that substitution that I was talking about. If you let this to be the denominator, then du is going to equal to dy, so that the differential substitution is going to be, just a du. But then I have a y over here. So what's y equal to? Y equals to u minus 4. So if I put u minus 4 up there, I'll have everything in terms of u. So u minus 4 minus 3 is what? U minus 7? Over u du. And now, because I have a u down in the bottom, that I can just, that's easy enough to split up. So I'm going to integrate 1 minus 7 over u du, and this is going to be u minus the integral of 7 over u, 7 ln of u, and then you replace it back with y plus 4. See? That wasn't too bad. Yeah, it was. Okay, well, that's how you would do that. Yeah. Oh, this one? I think when you eventually solve for this, you're going to have an ln of something, 7 something. Maybe. All right. I suppose I should finish this, huh? Finish what you started. Why don't you guys try the second interval while I take out my Wolfram alpha and you know, it's the same thing, right? See if you guys get it before I do. But it won't be fair if I'm stuck here. Get it? Did I beat you? Did you guys even try? Say it again? Yeah, it has to be the denominator so that it can the numerator can split up. All right. Well, you got something.
I got something that's happening X plus 6 over Y 2 7.
Okay, so this is what I got. I got x minus 7 ln of x plus 6 here. So that's my other side, and I'll keep my constant over here. So let's see. Let's continue on over here. I need to move some things here a little bit, rearrange my... So now I'll put this together. I'm going to get y plus 4 minus 7 ln of y plus 4 is equal to, and I just have an x minus 7 ln of x plus 6, and then here's my constant. Now, did I do that right? Yeah.
Why is this X plus 6?
Uh,
Minus 7.
Because I would do my u substitution as this. Yeah. So this is correct, right? Oh, because in your u substitution here, you're going to get u equals x plus 6, and then when you substitute that x equals to u plus something, looks like it'll just go away or something. I don't know. Should I do I need to do it? What? All right. I need to do it. This is the last time I'm going to do an integral in class. What? Did I do the y wrong? you know what they did? I see what you guys are saying. You know what? Yeah. You know what they did? Anybody? Can anybody guess? Because if I were to put this y equation over here in Wolfram alpha, it's not going to. I'll tell you what it's going to give me. This is what it's going to give me. So Wolfram alpha would give me y minus 7 ln of y plus 4 plus constant. Because 4 is a constant, and it merges it in together. So that's why it disappeared. But that's very alert of you. Good job, I guess. Okay? So that's what happened. So you're saying this should be an x plus something, right? X minus or x plus something? X plus 6 over here. So that 6 over here got merged in with that constant. So that's what happens. So I guess realistically we can get rid of this 4 as well and merge that in with a constant also. Okay, so do we want a merged constant, or do we want to pretend like we did it by hand? Let's merge a constant. So we're just dealing with y's. So we still have to put it in this form, and to do that, what we could do is we can put some of these things together. It looks like the x is in the numerator, so why don't I bring this x, this ln x plus 6 over to the other side, and I'll bring everything else to the other side. I'll bring, let me just tell you what I'm going to do. I'm going to bring this over to the left-hand side, so it's a positive 7 ln of x plus 6 minus 7 ln of y plus 4. And I'll bring this y to the other side, and then on the other side I have x minus y plus a constant. Yeah, so you could take this as a power of 7, and then you get x plus 6 divided by y plus 4. So with some ln rules that you guys, of course, remember, and if you don't remember, this is just a quick refresher. When you have a constant out in front of the ln, it becomes a power. When you're subtracting with ln's, then it's like dividing. And so you can put it all into one ln like this. And then you can take the exponential function, the e of both sides, they say. So you get x plus 6, y plus 4, 7 is equal to, now this has to be an e power, so e to the x minus y plus c. Yeah? C times e to the x plus y, so you can rewrite this as c times a different c, let's call it c1, e to the x, is that what you said? Yeah. I can go one more after that. C1 e to the x over e to the y. That should also work out, powers and stuff. Wow, we could type in all kinds of different answers for this. And let's see. Okay, is this good? Let's try it. I think we're wasting too much time on this. All right, I'm going to try C times E raised to the x minus y. Okay, that worked. Let me try something else. Let me try e raised to the x minus y plus c. That looks like it worked. What if we did the other way, where we kept the constants and didn't merge it? So that would be x plus 6, y plus 4. Okay, so all those work, and whatever works for you. Yeah. Well, as long as it's correct. Yeah, so in a test situation, I'll take a variety of things. That's why it takes me a little bit longer to grade tests. But I'll look at your work that you did, I'll look at your final answer, and, you know, I have a key, but in my key, I try to find the different scenarios and different looking answers. But as long as it's correct, then that's fine. Okay? All right. So I think that's about the most challenging type of separable differential equation you can get. Aside from that, we could do an initial value problem. This is an example of an initial value problem. So let's try an initial value problem. An initial value problem is essentially solving for the differential equation, except you're going to get a particular solution because they're going to give you a starting point, an initial value. So let's try number 7. Oh, I think I'm doing a lot of your homework here. First thing we need to do is to separate it and then solve it and then plug in the values to solve for the constant c. Let's see if we could do that. So dy dx, let's bring the y's over to the left-hand side. I can factor a y out. I suppose I should do that first. dy dx, y, and then a 1 minus x. And then I'll divide by y and I'll divide by x squared. So I'll have 1 over y dy is equal to 1 minus x over x squared dx. I probably want to split this up. 1 over x squared minus 1 over x dx. Okay, successfully separated. Now let's integrate both sides. Looks like I'm going to get ln of y on the first side, on the left side. Is this an ln of x squared? No. So be careful when you're doing, so we get carried away with the ln and stuff. 1 over cosine x, the integral of that's not ln of cosine x, right? So this is negative 1 over x, right? X to the negative 2. Wait, is that right? And then this one is the ln. And throw in your plus c. So solve for it now or solve for it later. That's your choice. I'm also taking a look at this, and they gave us negative values here. So, and I'm looking at our integral here. What am I missing? Absolute values. So we usually we begin to neglect the negative parts of things when we're doing indefinite integrals. But whenever we come up with an ln like this, the formula says we have to take the absolute value of it. So let's be careful, especially if we're going to start putting in negative numbers for x's and y's. So I'm going to solve for it here. Let's put in our value for x, which is negative 1, and our value for y, which is negative 4. So ln of 4, let's just make that positive, right? This is going to be 1/4. The negative x, the negative 4 in the denominator, and negative sign will cancel. And the ln, that should be a 1, right? Let's put in a 1. It's negative, but then I was going to cancel it with this negative. Well, let's cancel it with a negative there. And then ln of 1 is 0. And then this is a constant you're solving for. So if we solve for c, looks like going to be ln of 4 minus 1. Okay. Now that we have this piece of information, let's plug it back into there. And then we have the ln of y is equal to negative 1 over x minus ln of absolute value of x plus ln of 4 minus 1. So they want a y, so we should probably take the e of both sides. So y is equal to e raised to this whole thing. Oh, man. Which you can simplify a little bit, right? Yeah, you can simplify it yourself. So this would look like an okay answer, and you can simplify it. You can bring the ln's together, and then separate the e's so that you'll eventually have ln of or e to the 4 over x, I guess, maybe along the way. Yeah. I think so. Well, I suppose we could try it. So it's e raised to the, this is all in the power now. I'm going to put parentheses, and I'm going to type it the way I have it here. Let's see, absolute value. Nope. See my stuff now. No. No. Yeah, it's one of these are one of those things where you have to be careful about putting your stuff in the right place. All right, I think this is good. Let's see. At least this is exactly what I got, without simplifying it too much. Oh man. Four minus 1? ln of 4 minus 1, right? No, ln of 4 is together. 4 minus 1. What? Yeah, I think the absolute value needs to be there. All right, well, that was a mistake somewhere. This is where you like to say that the computer's wrong, right? All right. If you could figure out the answer before the end of class, I type it in, I get it correct, I'm going to get you a candy bar next time. So, Well, we could try to break this up, like I was saying, combine these two, although that shouldn't make a difference. I don't know. E to the negative 1 over x minus 1 times e to the ln, and then combine it. This would be 4 over x. And then that would just be 4 over x. Yeah, I think it should be, because they're assuming x is negative, so we're on the negative side, so it should still be that. All right, I'm going to try this one more time, and if it doesn't work, then I'll let you figure it out. So 4 over absolute value of x. And then let's get rid of all these things. So if they didn't take my first answer, then this is probably wrong also. Yeah. So I think we did something wrong in the steps previous to simplifying this. And whatever that is, like I said, if you can find it, I'll buy you a candy bar. If not, then I'll work on it this weekend and show you what we did wrong. All right, so let's put ... here to be continued. Because we need to take a look at our next technique. Okay, our next technique is linear equations. Well, that's not really a technique, that's a type of differential equation. But if you do have a first order linear equation, then there's a way to solve for this if you can't separate it. So our first thing that we should look for is to see if we can separate a differential equation, because that's the easiest type of solution that we can get from for solving a differential equation. If you can't separate it, then this is then you would hope that you have what's called a first order differential equation, and then you're going to see if you can solve for it this way. So if you have a first order differential equation, there's a nice systematic way of solving for this, and that is using the product rule. Remember the product rule? There's the old product rule from Calc 1, where the derivative of the first plus the second, or times the second plus the derivative of, yeah, you know what I mean. So what happens here is that if you look at a linear differential equation written in this form, it looks like we have the derivative of the second times the second, right? It's like this is f g prime plus f prime g, and for somehow you want to get the other two things to cooperate with you to make it look like it's what it's supposed to be. So what we're going to do, and this is one of those things where it's more or less like a proof. It shows you step, but after we do this, we get a formula. I think knowing the steps of how to do this generically is good, and then later on, we're just going to rely on the formula. And you'll probably forget these steps later on anyways. So what we'll do here is let's first divide everything by a sub 1, which is a function. Let's get rid of that. So we have dy dx is equal to, is plus a sub 0 ax divided by a sub 1 a times of x, and then y is equal to g of x divided by a1 x. Okay. This looks a little complicated. Let's rewrite this as a nicer function. Let's call it p of x. I guess we should also call the second one q of x or something, because it's just a function. Now, if this is supposed to work as a product rule, we want something here to multiply this by something like so that this is going to be p of x, right? Wait, uh-oh, am I doing this right? Yeah, I better look at my notes. Yeah, it's kind of on the right track. Why don't I just copy my notes? So what we want to do is we want to make the left-hand side look like a product rule by multiplying by some factor. And that factor is actually called an integrating factor. So if you can multiply this equation at this point to make it look like to make the left-hand side look like a result from a product rule, then that means if it's a product rule of something, then you can undo that derivative, because that's just a derivative of a product, right? You can just undo that derivative by taking the antiderivative, the integral of it. And so that's the key. Which means we have to find out what that integrating factor is. So to make that integrating factor look nice, let's see if we can figure out that integrating factor. Uh-oh. So we would integrate both sides. We should get something like this. And then if you solve for mu itself, the integrating factor, then it's like taking the antiderivative of that. And so our result here is that we get to an integrating factor if we multiply the original differential equation, or the differential equation where you have dy dx by itself. If we multiply that whole differential equation by this, it should become then a perfect product rule. Okay? So this is your final result, or this is your key. And if you have a first order differential equation, you can always multiply by this factor, and then you should be able to solve for your equation. All right, let's see if we could do an example. Should we do another homework problem? Or let's... Okay.
I get my candy bar.
What kind of candy bar do you like?
I'm not
All right, let's do an example of this integrating factor business in the first order differential equation. So this is one of the simpler types of first order differential equations that we can come up with. So you have to convince yourself that it's a first order. Yeah, it's dy dx, that's the highest derivative. It's a linear. I got the dy dx and the y. There's nothing being multiplied by that, so there's no other issues. So this is a first order differential equation. Now we identify some of those key functions that are involved here. If you look at our formula for a first order linear differential equation, we have dy dx plus some function times y plus another function. Okay? So what's our p function? That's actually the most important part of this, is identifying your p function. What's our p function in this case? It's just a constant 1. So that's the function that we're looking at. Okay? Now, according to the formula, our integrating factor is actually, I don't know if you noticed, I didn't really say much about that. Our integrating factor is an integral of the p function, but put as a power of e. Okay, so it's e raised to the integral of your p function with respect to whatever the independent variable is. So that's just x, right? The integral of 1 is x. So this is e to the x. Now, normally we would do a plus c, but there's all kinds of other plus c's that will come up. So I can put a plus c right now, and then we'll watch it eventually get kind of merged into the other c. So let's see what happens to this plus c, because whenever we take integrals, we should think about a plus c. Indefinite integrals. So this says that we need to multiply this differential equation with the integrating factor. So multiply the whole equation by your integrating factor mu. So this is e to the x plus c times dy dx plus e to the x plus c times y is equal to e to the 4x times e to the x plus c. Now the whole key in doing this integrating factor is that so you can look at the left-hand side as a product rule of something. So this is actually d dx of something. What is it the d dx of? It looks like e to the x plus c times y, right? So if we take the derivative of this product, e to the x plus c times y, we should get this thing. So what we're doing is we're kind of undoing the product rule because we're going to take the integral of this. Is that okay? Okay, now the other side we end up with e to the, we multiply this, don't we? Or do we add them? We add the exponents? Add? Okay. So 4x plus x is 5x plus c. By the way, did I tell you that c is not important here? I'm carrying it around. I want to get rid of it now. But I'll finish this and see. All right, let's integrate both sides. Now with respect to x, and let's see what happens. So the antiderivative, the integral of a derivative is the original function. And there's the y that we're solving for. And the antiderivative of this is 1/5 e to the 5x plus c plus another constant, right? Let's call this constant d. Yeah, I hope so. So when we divide both sides, we have to divide both sides here. We get 1/5. Oh, there's a lot of algebra here. 5x plus c plus d all over e to the x plus c. Oh. All right. So let's see what happens to this thing. So let's have we need to split this up, right? So it's a 1/5, and then we have e to the x plus c. Let's rewrite this as another constant, a, divided by, that's also the same a, right? Well, the a's here will cancel. We got rid of that. And then this one is d over another a, e to the x. So if we let our a equal to e to the c, those are where all the a's came from. And then if you simplify this a little bit more, we get e to the 4x, and then dA can be merged together as another constant. Let's call that b. And then, so we end up with one constant, and that one constant, the constant that was attached to this kind of got together over here, and then they cancel each other out. And then the other constant that would have went with this constant kind of merged together here into one constant. So what that tells us is that this c over here, the plus c that we did when we did our integrating factor, this plus c over here that we got when we integrated isn't going to make much of a difference for us in the long run. And so the constant that would come up here would have merged for that constant that we would have gotten when we do the antiderivative on the main part of the equation. So the lesson here is we don't need this constant. So when you find an integrating factor, you're going to do an indefinite integral, but you're eventually going to do another indefinite integral in the problem where those constants will eventually merge. So you don't need that first integrating, the first constant of integration. Okay? All right, so this is one of the first real, the separable differential equations technique. It's really just doing some algebra and then doing our calculus of taking the antiderivatives. So it's just really still an exercise on antiderivatives. This is the first real technique that's actually new to us that we haven't seen in calculus before. It's looking at the first order linear differential equation and then using a technique where we have to find an integrating factor, and in finding that integrating factor, we can rewrite our differential equation as a product rule, and we undo that product rule by taking the antiderivative, and then that's where we solve for our function. So really, this is the first technique that's learned in differential equation that's not in the previous calculus classes. Okay? All right, this should get you going with your homework assignments. If you haven't gotten the key yet, it looks like it's available at the bookstore. Get your web assign access so that you can start doing your homework. And I'll start putting up the due dates over the weekend.
You don't need it after
Thursdays.
You don't need it after the LM because